At the beginning of Chapter 10, we mentioned that our atmosphere was mostly comprised of a mixture of gases, mainly nitrogen and oxygen, and a few of the noble gases. But look, we also have a little bit of water vapor present in our atmosphere also, and that does contribute to the overall pressure exerted by our atmosphere. In the early 1800s, John Dalton studied the properties of air, and what he determined was that in a mixture of gases, each gas in the mixture exerts its own pressure. And the total pressure of the gases in the mixture is equal to the sum of the pressures that would be exerted by the individual gases if they were alone. We refer to this relationship as Dalton's law of partial pressures. And mathematically, we would express it as such. In other words, the pressure exerted by the first gas combined with the pressure of the second gas and the third gas, and however many more gases there are in the mixture, each of these is exerting its own amount of pressure, and we can add those pressures up to give us the total pressure of the mixture. At sea level, the nitrogen gas in the atmosphere exerts a pressure of 593 torr. The oxygen that's in the atmosphere exerts a pressure of 159 torr. And that makes sense because remember, we have a lot more nitrogen in our atmosphere than we have oxygen. And there's a small amount of carbon dioxide as well. And so if you add up all of those pressures, you get 752.3 torr. Now remember, at sea level, standard pressure is 760 torr. The rest of that pressure, the difference between these two, is water vapor. Now the amount of water vapor is going to vary depending on the temperature of the atmosphere. The higher the temperature, the more water will vaporize into the atmosphere, so the higher the vapor pressure. If we know the total pressure of gases in a mixture, we can use Dalton's law to determine the partial pressures of each of the gases in the mixture. But we can also determine those partial pressures if we know the number of moles of gases present in the mixture. Mole fraction is a dimensionless number that expresses the number of moles of a particular gas to the total number of moles in the sample. It's just like looking at a percent, except that we're not going to multiply by 100. Let's say that we have a mixture of gases that contains helium, neon, and argon. And the total pressure of the gases in the mixture is 3.34 atmospheres. And Dalton's law tells us that total pressure is coming from the pressure exerted by the helium, plus the pressure exerted by the neon, plus the pressure exerted by the argon. And since each of these gases makes up one part of the total, we can use mole fraction to determine how much of a part. So the first thing we'll do is find the total number of moles by adding these together, and we get 0.956 moles. So remember, we're taking the part, the number of moles of helium, and dividing it by the total number of moles. And so taking our moles of helium and dividing it by the total number of moles, we get a mole fraction of 0.563. We'll do the same for neon. Dividing moles of neon by the total number of moles, we get a mole fraction of 0.329. And then finally, we'll do the same for the argon, giving us a mole fraction for argon of 0.108. And if you add all of these up, you'll get a total of 1, just like percents would add up to a total of 100. And multiplying the mole fraction of a gas by the total pressure of the gas will give us the pressure that that gas is exerting in the mixture, or the partial pressure of the gas. So the partial pressure of helium then is going to be our total pressure, 3.34 atmospheres, times our mole fraction gives us a partial pressure of 0.188 atmospheres for our helium. We'll do the same for neon, giving us 0.1099 atmospheres for the partial pressure of our neon. And finally, our argon, we get 0.361 atmospheres. And if you add those all together, you'll find that they add up to our total pressure of 3.34 atmospheres.